this unit, we're going to continue our look at number sense. In this lesson, we're going to look at the number systems and radical and exponential forms of a number. All right, hi everybody. So in this lesson, we're going to take a look at number systems, and then we're going to take a look at radical and exponential forms of the same thing, basically. We're the same expression here. And you'll see what I mean by that in just a minute here. First of all, we're going to take a look at number systems. Okay, so the natural numbers are basically your counting numbers, the ones that you would have learned when you were just a little person learning how to count and your ABCs and whatnot. So 1, 2, 3, 4, 5, so on and so forth. Okay. Then we move on to the whole numbers, and the only difference here is the zero. We're going to include the zero in there, and the inclusion of the zero is actually quite significant. Okay, having that zero in the number system there, that digit that represents nothing. Okay, really significant move forward in mathematics, and with that, it opens up the door to integers. Okay, and so integers, we're including the positive and the negative numbers. So now we're going both sides of zero, right? And we can go infinitely in either direction. But we're still talking about complete values. We're not including fractional values at that point until we get to what we call the rational numbers. Now, up to this point, this might make a lot of sense to you. N for naturals, W for wholes. Now, we're using I for integers, although just a little heads up here. Actually, the symbol that typically gets used is going to be Z. Okay, later on, kind of beyond this course, beyond into like university or whatnot, you'd start using Z to represent the integers. There's a good reason for that, and I'll let them explain that later. Here, though, this one maybe doesn't make a whole lot of sense. We're going to use Q for rationals, mostly because we're going to use so we're going to use R for something different here in just a moment. But rational numbers are going to be any number that can be written as a fraction, okay? Integer divided by integer. Now, you may have talked about these before. These are your terminating decimals or the repeating decimals, okay? And so, yeah. Anyway, that's basically all you really need to know there. Then you've got the irrationals. And I love this. This is a Q with a bar over top. And this is classic. I love the way mathematicians kind of work this one through or explain it here. The bar over top is a negation. Okay? That little bar over top negates whatever's underneath it. So if Q is rational, this symbol literally means not rational. What a great definition. You identify what the rationals are. The irrationals are the numbers that are not rational. Love it. But these are your non-terminating, I pointed this, non-repeating, non-terminating decimals. They go on forever without repeating any specific patterns here. Okay? And so as soon as you start taking the square roots of numbers that aren't perfect squares or cube roots of numbers that aren't perfect cubes, you're going to end up with irrational numbers. So you got numbers like pi, root 2, or those are your kind of classic examples of those. Then we move on to the reals, and we're going to use R to represent the reals. And that includes everything above. All the numbers that we're discussing are going to be real. Now, that might kind of naturally lead you to ask, well, wait a minute. That's an interesting thing to explain, to call it here. Those are the real numbers. Okay? So is there something there that isn't real? And the answer is yes, there is. Okay? There are other numbers that there's another system out there of numbers that is beyond this, and we're going to let them talk about that later on. You get what we call these complex numbers, and they are based on one little guy here called an imaginary number. And that is the symbol I. And I'm not going to worry about that right now, but it's just worth mentioning that when we get down to here, we call it real because there's this other number out there that we call an imaginary number, and we build a lot on top of that as well. But that's for later. Okay? So everything up to this point here is real numbers here. And so you might have a sense of this relationship here. You've got the natural numbers, and then you get the whole numbers. And the whole numbers basically include the natural numbers plus the zero. The integers include the natural numbers, the whole numbers, plus all of the negative numbers. Okay, all of the negative naturals there. Now the rationals encompass everything inside there. And the reason why that's true is because, let's say, for example, we take the number 5. Well, I can write the number 5 as a rational by dividing it by 1. And because I can do that, basically all of these numbers inside here, the naturals, the whole numbers, the integers here, those can also be considered rationals. But the irrationals are different. Okay, the irrationals are different. Then there is no overlap here. So a number is either going to be rational, fall into these categories here, or it's going to be irrational. And then we put this big around the whole thing, and then these are our reals. So the real numbers include both the rationals and the irrationals. So now we're going to take a few moments here and we're just going to classify some numbers. Okay, so this question says, place a check mark in each family of numbers that the numbers belong to, okay? So for example, negative 96, is that a natural? Well, no. No, it's not a natural because it's negative here. It's also not a whole, but it is an integer. It is a rational. Now, it wouldn't be irrational because if it is rational, then it can't be irrational and vice versa. But at the same time, it is real. Now, 0.6 repeating, okay, this is a fractional number, so it's not natural, it's not whole, it's not an integer, but it is a rational. And then it's not irrational, but it would also be real. 0 is not a natural number, but it is a whole number. By that token, then, it's an integer, and then it's also rational. It wouldn't be irrational, but it is real. Now, negative 7.47487. Now, what I'm supposed to interpret by this is that the decimal here is not repeating, and then it's not because of the dot, dot, dot here, it's also not terminating. Okay? Now, that's a bit of an assumption because I don't know what else is going on beyond this, but that's what we're supposed to assume by that. If I don't see a pattern here, I'm supposed to assume that that there isn't one that exists. So it's not natural, it's not whole, it's not integer, and it's also not rational. This is definitely irrational. But it would still be real. This one right here, 7 over 2, that is written in the form of a rational, okay? Now, but 7 does not divide by 2. If it did divide by 2 nicely, then I could probably fit it into these some of these number systems as well, but it doesn't. It's going to be 3.5. Because it's rational, it's not irrational, but it's also real. Negative 4.18, and notice that it's 18 repeating. So again, I've got this decimal number that goes on forever, but it is repeating. So that makes it rational. And it's not going to be natural, whole, or integer because, again, it's got this decimal value to it. It won't be irrational, but it will be real. Now, don't get thrown off by this one. 5.2173. Granted, there's no repetition here, but it terminates. I don't see the dot, dot, dot after that. So this is a terminating decimal. It won't be natural, whole, or integer, but it's rational. So it won't be irrational, and it will be real. Okay, square root of 25. Now, it helps to be able to evaluate that, and in fact, we can, and I get 5. The square root of 25 is 5, and that is natural, it's whole, it's an integer. As a result, it's also rational, okay, because remember, we're still talking about rationals. That means it cannot be irrational, but it would be real. Now, the square root of 7, on the other hand, the square root of 7, well, 7 is not a perfect square. And so when we were talking about this before, when that's the case, I am going to get a non-repeating, non-terminating decimal, which puts that as an irrational. And again, it would still be considered a real number. Okay, so there you go. Now, when it comes to that last little bit there, taking a look at those square roots, could be cube roots, fourth roots, or whatever, it helps to be able to go to the calculator and figure out, by looking at the decimal, whether or not a number falls into those categories here. So we need to be able to take the square root. If you're dealing with a TI-83 or an 84, and we're trying to figure out what these roots are, to get a cube root, okay, you would press the math button, okay, math. That opens up this menu right here. Number 4 is going to be the cube root. And if it's something larger than that, then what you do is you press the number for the root that you're looking for. Let's say you're looking for a 4th root. So you'd press 4. Then you'd press math to get into this menu. And then you'd come down and grab this tool right here. Now, let's take a quick look. We're going to use the calculator to determine whether these numbers are rational or irrational. Now, bear in mind, once again, we're not trying to trick anybody here. We just want you to have a quick look. If you don't see a pattern, then you can assume that it's irrational at this point for what we're looking at here. So, to start off with, we're going to take a look at the cube root of 9. So press my math button. I'm going to go down to my cube root, enter in 9. Okay, and I get a non-terminating. I'm assuming that the decimal goes on forever. Okay, if it would have stopped, I would assume it would have stopped earlier than this. So this is non-repeating, non-terminating, I'm assuming here. So this is going to be irrational. The square root of 14. So square root of 14. Yeah, I'm not seeing any repetition there, so I'm going to assume. And this goes right to as far as the calculator will give me those decimals. So I'm going to assume, once again, that's irrational. Square root of 4 divided by 9. Oh. Now, that is a repeating decimal. Now, I notice you see that 7 at the end here, but that's because the calculator rounded that last digit. This is actually going to be a repeating decimal, so that's going to make it rational here. Now, the interesting thing about this is, one of the things I can do to really double check this is if I press the math button, the very first option I get is to convert to fraction. And notice that I can take that number and convert it to a fraction, which automatically makes it irrational. But let's go back up a little bit. If I do the square root of 14, can I convert that to a fraction? The answer is no. Now, this isn't perfect by any stretch of the imagination. This is not a perfect way to make that conclusion, but it would work for a lot of the numbers that we're going to use at this level. The cube root. So math, cube root of negative 125, press enter. Oh, and I get negative 5. Okay, that is actually an integer, which makes it, by default, irrational. Square root, whoops, the square root of 1.32. Okay, well, I'm getting a decimal there that looks like it's not repeating. Looks like it goes right to the end here, so it's going to be non-terminating. So that looks to me like that's the intention is that that's going to be irrational. And now the 5th root of 32. So to get the 5th root, I have to enter the 5 first, math down to this xth root. And notice in this case that my calculator actually puts the 5 up as the root index here. Not all calculators will do that. Some of them will just write the 5. Like some of them will write it down as 5, and then you'll see this xth root like this, and you'll put the 32. In any case, press enter, and I get 2, so that means that this is going to be rational. Okay? So anyway, don't try to overthink this. Okay, we're not trying to trick anybody, so if you don't see a pattern and you see that you get as many decimal places as the calculator can give you, it's fair to assume at this point that that's going to be an irrational number. Okay, now for a moment we're going to take kind of a sideways step here. We want to take a look at something else here. I want to show you the relationship between a radical form of a value and the exponential form of a value. Show you how these are related. And basically the rule is this. If I'm taking the nth root of a number, another way that I can write that is that number to the power of a fraction 1 over n. Okay? So for example, the third root of x could be written as x to the 1/3. Now I'm going to sort of explain why that works, although I'm not going to spend a lot of time on that. But just note that the index becomes the denominator of the fractional exponent. So the root index becomes the denominator. Okay? The exponent on the radicand becomes the numerator of the fractional exponent. So, okay, again, because this is to the 1, that's why that's to the 1 up there. And the base is the radicand. So, for example, the square root of 7 is 7 to the 1/2. The cube root of 2 is like 2 to the 1/3. Now let me let me try to at least explain a little bit as to why this works here. Watch what happens. If I take root 7 and multiply it by root 7, I get 7. That's because that's what a square root is. If I take a square root and square it, multiply it by itself, the square root goes away and I get that number. If that's not clear to you, think about it like this. 3 times 3 is 9. Whoops. 3 times 3 is 9. 3 is the square root of 9. And so that's the pattern here. When I multiply the square root by itself, I get the original number. So root 7 times root 7 is going to get me 7. Now, if it's a cube root, it's a little bit more, there's a little bit more involved. Squaring won't do it. I got to cube it. So the cube root of 2 times the cube root of 2 times the cube root of 2 is 2. Now watch what happens. If I take 7 to the 1/2 and multiply it by 7 to the 1/2, when you multiply two powers together, and I hope you remember this, you add the exponents. The base stays the same, you add the exponents, so it becomes 1/2 plus 1/2. Well, 1/2 plus 1/2 is 1. So this is 7 to the 1. Now take a look at this. Root 7 times root 7 equals 7. 7 to the 1/2 times 7 to the 1/2 is equal to 7. When I squared this, I got 7. When I squared that, I got 7. I'm doing the exact same operation. I'm squaring these guys and getting the same result. They must be equivalent. Okay? Now, that's, again, what I said there is not 100% true. I mean, you could play with negatives in there and whatnot, but I'm hoping that the essence of the idea is getting it through here. Here, notice I've got cube root of 2 times the cube root of 2 times the cube root of 2 is equal to 2. And again, this is like finding a volume calculation. It's basically the same thing. Okay? If I multiply this 2 to the 1/3 times 2 to the 1/3 times 2 to the 1/3, this is like 2 to the 1/3 plus 1/3 plus 1/3, which is equal to 1. So 2 to the 1, and it's the same thing. When I cubed this, I got 2. When I cubed this, I got 2. That means these things must be the same, roughly speaking. So I don't want to spend too much time going over that. Now let's take a look at some questions where we go back and forth between these two different ways of writing these relationships. Now let's take a look at some questions here. This one says, express each of the following exponents in radical form and then evaluate. Okay, because yeah, it might not be abundantly obvious what 64 to the 1/2 is, but in radical form, the base becomes the radicand, okay, and the denominator here is going to become the root index. It's going to become a 2, a square root, and 64 to the 1. So this is asking for the square root of 64, and I think about that for a second or two, and I know that the answer is going to be 8. This is going to be 32. This is going to be a root of 32 to the power of 1, and the denominator becomes the root index. This is the 5th root of 32. So when I go to my calculator, type in 5 to get and then go and get my answer there. And I'll just do that with you guys right now. So it would be 5, press math, go down to that xth root, 32, and I get 2. My answer is going to be 2. Here, this is going to be the cube root of negative 216 to the power of 1. Now, if I'm going to put a power on there as well, if I'm going to put an exponent there, I really do need to put parentheses. And I can go to my calculator, enter that in, and you're going to get negative 6 as a result. And then here, this will be the root of 16 to the 1, and it's going to be the 4th root. So again, I can enter that in my calculator, and I will get that the 4th root of 16 is going to be 2. We keep going. And it doesn't matter that the base is a fraction. This becomes 16 over 81. This will be the 4th root here. Again, it makes no difference. I'll enter this into my calculator, and I am going to get, in fact, this one here I probably should do, just so that you can see what's going on. This is going to be 4 math down to the xth root, and I'll enter 16 divided by 81. Now when I press enter, notice that I get a repeating decimal. But I know that I can convert that to a fraction by pressing math to fraction, and I get 2/3. And so my solution here is going to be 2/3. Here, To the 1/2 means it's going to be the square root. Okay? And the square root of 4 is 2, and the square root of 9 is 3. So this is also 2/3. These guys are equivalent to each other. Once again, to the 1/2, it's going to be the square root. The radicand is the base of the power, so square root of 100 is just going to be 10. And then because there's a 3 in the denominator, this is a cube root of the base, -8, and this is to the 1. And actually, I probably should have been putting to the 1 on all of these. And the cube root of -8, if you go to your calculator, you will get -2. Okay, and there you go. So I hope this idea of going from that exponential form to the radical form makes sense.